Okay, the last one is the most thought-provoking as far as the examples that I'm going to do that relate to your homework. And this is based on number 13. All right, here it is. Here's what they say. F is defined to be the magnitude of R times R. R is the vector x, y, z. S is the hemisphere z equals square root of 1 minus x squared minus y squared, and the disk x squared plus y squared is less than or equal to 1. And they want you to find the flux. Let's try and draw S first and see if the div theorem, right, divergence theorem, will apply. This is the top half of a sphere, isn't it? Because if I square both sides, I get z squared. If I move all my variables to one side, I have the equation of a sphere. But because it's solved for z, it's only the top cap. So I know I've got the top cap of a sphere of radius what? 1. And then that's the top of it. And then the bottom is the disk that is the base of it, right? Pardon?
Do we have to add it?
What do you mean add it?
Like, because aren't they two close surfaces?
They are two separate surfaces which enclose a solid.
Okay.
Okay? I think the book also says that this is in the xy plane, which means that because if I don't say this is in the xy plane, this is actually a solid. It's like a cylinder, right? If that was equal 1, that would be a cylinder. Less than or equal 1, this would be like a solid bar. But if I say it's in the xy plane, it's just the bottom. Understand? Any questions on what S is? We're all right? So E is the solid it encloses. We have that. We have an E in here. So I should be able to use the divergence theorem, but I'm going to need to come up with the div of F to do that. And we need to get a grasp on what F is, because F was not given to us in its standard form. So what is it? F is actually this vector. So this is like my PQR. Not yet, though. This is the like the vector field, but we're multiplying it times the length of the vector. That's what F is. So it's like a position vector, right? X, Y, Z is where you are, times how far away you are from the origin. So you're scaling it by how far away you are. That's the field. So I'm going to rewrite this in terms of X, Y, and Z. What is the magnitude of R by definition? Square root of x squared plus y squared plus z squared. That is just a number, isn't it? That's just a number? Okay. And then we have times the vector r, which is x, y, z, right? That's what that means. And since this is just a number or a scalar, I distribute it through to each component. So this becomes x root x squared plus y squared plus z squared, y times root x squared plus y squared plus z squared times z comma z times x squared plus y squared plus z squared. That's my vector field. It's ugly. I'm going to still go for this. I'm going to try and get its div. So I need to take some partial derivatives and add them all up, right? Let's talk just about this one for a second. what would the partial with respect to x of this be? Because that's what I'm supposed to do right now, right? You would have to use product rule, right? We have a product happening right here, and chain rule. So let's try it. What is the derivative of x with respect to x? 1 times this, right? So I'm going to start abbreviating this to make this easier, all right? This is going to be 1 times the root of all this stuff, junk. I'm going to call it j. I'm even going to get more lazy. More lazy? Lazier? More lazier. You know what I'm saying, right? Root of, I'm not even going to write the word junk. I'm just going to write j. Okay? Plus what? What's the derivative of the square root of some... Okay, x, you want me to put the x first? Okay, x. Derivative of the root of something is 1 over 2 times the root of that stuff, right, the junk, times the derivative of what's inside of it with respect to x, which is just 2x, right? The 2's cancel. You all okay? So I get this. I get root junk plus x squared over root junk. Is that all right with you? I'm just going to leave it like that. I could get common denominator and all that, but is it all right if I leave it like that? Okay, now this is the partial with respect to x. The only difference between this and this is there's a y here, but I'm differentiating with respect to y, so everything should be exactly the same except y squared, and the last one should be everything the same except z squared, right? That'll be nice. So with that in mind, the div of f should be this root junk plus x squared over root junk plus root junk plus y squared over root junk plus root junk plus z squared over root junk. You can write junk. Yep, that's okay. Yeah. All right. What can I do here? I've got 3 things that are identical. Root, root, root. So 3 of those. So this is 3 roots of junk plus, and then the things that remain all have a root junk on the bottom, right? So I can combine them together into one fraction, and I'll have root junk on the bottom, x squared plus y squared plus z squared. But what is x squared plus y squared plus z squared? That is the junk. That is the junk, isn't it? Yeah? So I have 3 root junk plus junk over root junk. And what's junk over root junk? It's root junk, isn't it? So this is 3 root junk plus root junk, which is 4 root junk, which now I'll actually write in what it is. There it is. Okay, so any questions? I look at this and I say, crap, man, well, I really don't want to integrate this because, right, this is going to be our integrand. But look at our region, E. How can I represent that region? Spherical coordinates, right? That's perfectly suited for spherical coordinates, isn't it? And if I go to spherical coordinates, what is x squared plus y squared plus z squared? What is this? That's rho squared, but then square root. So that's just rho, isn't it? This is just 4 rho. That's all that is. With me? All right. Hope so. So here's what I've got now. I've got my triple integral over E of div f dv. I'm going to switch to spherical here. Remember all our spherical conversions? It was like x was, I don't know, like rho cosine theta cosine phi. We used u and v also. And then y was like rho sine theta sine phi. This isn't right. Something's wrong. No? Phi. Phi or phi. You'll hear people say both ways.
Because I said V and then they're like, oh, it's fine.
Who said that?
Some people.
I've said it both ways. You'll find people in the math community that say it both ways. Like they'll say it one way and they say, that's the way. And then you see someone else, no, it's the other way.
You know that honor society, they Phi Theta Kappa, and so I said that. And
Yeah.
they're like, oh, it's Phi Theta Kappa. Oh, good for you.
Yeah,
Whatever.
I know. Yeah, it's just one of those things, man. It's like Euler and Euler. You'll hear, there's a mathematician, Euler, Euler. You'll hear people say Euler. I believe Euler is correct. But I think phi and phi, you're okay either way.
Though they kind of raise a valid point, then is it Wi-Fi?
Wi-Fi? They asked Wi-Fi?
Yeah, is it Wi-Fi?
Why?
It's
All right. Yep. Rho sine phi phi. We'll call it phi phi instead. Okay? Yeah, that's why I was saying this wasn't right. Something wasn't right here. Okay, sine. Yeah, there we go. All right, that's our conversion. Now, if we're going to use this conversion, if we want to draw this solid, right, using spherical coordinates, give me the restrictions on those variables. Let's start with rho. We can start with any of them, but what did I do? For what? Did I write it down wrong? Jeez, what's going on here? Well, you know what I was thinking of? I was thinking of what we have to include in our integrand. No excuses, except that it's the last day. All right, so there's our spherical. We don't actually need any of this right now, right? I mean, we just need to find restrictions, which means we need to know, back here in this hemisphere, rho was the radius. It was the distance from the origin out to my points. And if I want the whole solid, I want to go from 0 out to, well, this is a unit sphere? Yes, it is. How do I know it's a unit sphere? Square both sides. Move the variables over. You can see your radius there. Okay, so I know that rho has to go between 0 and 1. Theta. Theta is the angle that swings you around like this, right? 0, 2 pi. And phi phi is from the z down, right? So z down to the xy plane. I want that 0 to pi over 2. There we go. That should draw it. So we've got triple integral. I'll put my limits of integration in just a second. I need to do the div of f, which we turned out determining was this, right? X squared plus y squared plus z squared, we said was rho squared and then square root. So this is 4 rho. But every time that we do a spherical conversion, we must include rho squared sine phi phi. I like that. That just has a ring to it. Phi phi or phi phi? Phi phi? Phi phi? Faux fum? Everyone got this? This is the actual div f. This is what we have to put because we went to spherical. And finally, my variables. Doesn't matter what order, right? D rho, d theta, d phi phi. And you've got 0 to pi over 2, and 0 to 2 pi, and 0 to 1. Dot, dot, dot. dot, dot, dot. Yeah, you could split this up because your rows are separated from your phi's, and so the answer here is 2 pi. Nice clean answer. All right. I like that one. So it's highly unlikely that you're going to see a problem directly out of the section for spherical coordinates if I can ask you a div problem that requires you to go to spherical coordinates, right? Your final is going to be one problem. And it's going to kill 32 birds with one problem. No, I'm just kidding. All right. Yeah. Okay, this is the last thing I'm going to show you this semester. This is going to be, well, probably take me about 20 minutes. We'll see. Maybe not. So I'm going to start off with just setting up some concepts we're going to need for the problem. This is not a problem that I would ask you on the test. This is more just kind of, this is kind of cool stuff that has to do with divergence theorem. So let's say that we have, I'm going to do a different color here. Let's say that we have a surface, three-dimensional surface, all right? So this has, it's three-dimensional. I'm just doing that so you can kind of see it has some depth to it, all right? I'm going to call this surface S2. And that surface S2 encloses a solid, doesn't it? I'm telling you it's closed, all right? All right. Now, inside of S2, inside of S2, I'm going to draw another solid, another surface, which again is a closed surface. And I'm going to call this one S1. It's inside, though. Yeah, okay, yeah, jelly-filled donut. There you go. That works. Except there's no hole on the outside where this can start spewing out. But yes, same principle. Remember, you're talking to someone who spent a year talking about the difference between a coffee cup and a donut. So, all right, so you see the picture? Okay? Now, the normal vectors on S2 point outward, right? Like this, away from the solid. That's our standard orientation of the normal vectors of S2. I'm going to call these n sub 2 to stand for the normal vectors for this surface 2. The normal vectors for S1 in standard position would point away from the solid also, right? So the normal vectors for this one would point away, all right, like that, yes? And there's more on the other side, and they're pointing away from the solid. With me? So the vector, if I take this vector and I point it inward, right? Take this one and point it inward, that would be the opposite orientation, wouldn't it? And that vector that points in would be negative n1, wouldn't it? Okay. Understand the picture of what's happening here? Yeah? So I want you to consider right now E, a solid that is the solid between the two. That's the bread of the jelly-filled donut, right? That's the part I'm talking about. All right, consider that solid. And consider the surface that would enclose it.